All right, welcome back. Okay, so we are gonna have our next speaker today. The speaker is gonna start at around 6:30ish, and he's from ABS Consulting Company. So he essentially travels the U.S. and like trains a lot of professionals on like doing root cause analysis and conducting and performing like fault tree analysis. So it's like rare opportunity that he's like working from our backyard, and he's making the time to come to class to essentially share his experience and like with us and essentially like give us a workshop on that. So that's gonna happen the second half of the class. The first half, we're gonna continue with our own class. I'll start with reviewing a little bit, going over the exam, and then we go through the new material. So it hasn't, most of it has been graded. It's not done yet. So hopefully you'll hear back in, I would say a day or two, give or take, or maybe a little bit more. And again, regardless, don't panic. There are a lot of opportunities in this. Again, I don't think the exam were too bad. So let's. I don't know about the grades though at this point. But then there are a lot of opportunities for gaining back if you have lost things. Gaining back, right? We have up to 5 points bonus through attending these lectures. So that's plenty already. If it's not enough, I have decided to drop the least homework for like the least homework, I'm gonna drop it. So if you turned in something late, which wasn't accepted, or you messed up one homework, don't panic. When I'm grading, I'm gonna remove one homework, which was gonna be your least homework grade, when I'm adding things up. So hopefully like all of these are gonna add up and help you in case you have missed something. But let's take a second and go through the exam, the structure, because at least I believe when I was writing it, I believe it was very similar to what you had seen before. The problem is if you missed something or something happened, the problem is I don't know how many of you had taken open everything exam before. It's not very common, right? So I don't know. When I was a student, first time I took an open note, open book, open everything exam, I essentially was like, oh, I have everything with me. So let me just maybe like I have a lot of other assignments. Let me like prioritize those and kind of like this, I have everything with me, right? Which is not the best strategy because you know you have time restricted. If you had 2 days with all your notes, you could just write everything off of the notes, right? You knew that you'd seen these, but you just didn't know where to find them. So essentially the point of like making these open note, open book is for you to not memorize things, not to come to exam and figure out where things are. So we should study as if it's like, oh, closed book, closed note, close everything exam. The only difference is now you don't need to memorize stuff, right? So when you're studying for the final exam, which is going to have the same format, right? Make sure you study as if it's a closed book, closed everything kind of exam, right? And that way you are fully prepared. And you just, again, I could make this closed book, closed note, everything, and ask you to bring a cheat sheet, like with just a formula, because that's essentially what you needed. But I figured you can have everything with you, but I didn't want to make it more difficult than it should be. So I would like to give you another like open note, open book, open everything exam, the final exam. So I don't want to make it like closed book, but make sure you study as if it's closed book, right? Make sure you know where things are. Make sure you work through homework exercises, because a lot of the exam questions were like essentially borrowed from homework. Yes, they were a little more complicated. Okay, it's exam, it's supposed to be, and they were like maybe like multiple parts to every like question, which I'm gonna reduce the number of, because I got this feedback that there will be maybe a little bit like instead of having 4 parts per question, maybe I can do 3 per question or something like that, because I want to go in depth, but maybe like having too many parts for like one question, maybe that was too much. But again, make sure you study as if it's closed book, closed notes exam. Okay, so this exam had 100 points, 6 questions, 5 computational, and 1 true false, essentially. Each of the true false were worth 2 points. Each of the computation questions had multiple parts, and each part had 5 points. Okay, so grades will be posted soon. As everything else, you're going to have 2 weeks to go see your TA, go see your exam, make sure you understand what you missed. The final exam is going to be comprehensive. So the final exam is going to be comprehensive. So you're going to be tested on the material that you were tested on the first part, and you will see why. It will make sense as we go through we start with our class today. You will see why you will need to know what is the Weibull distribution. You cannot just forget about those concepts. So make sure you go see your exams. All right, let's start from like some of the questions that I thought may be like more difficult, or we may need to like revisit them in class. So okay, probability density function can be larger than 1. True or false? Remember when we said, oh, there's my pen. Remember when we said the only thing that matters is the area under this curve, not the curve itself, right? So what does that mean? We essentially, I remember we drew things when we said this is 1, and the distribution can very well go beyond 1, right? As long as the area under the curve is 1. So the density can go above 1, right? But then not the area under the curve. So that settles that, right? The probability density function can be larger than 1. That's true, right? And everybody got variations of this question. What about the reliability function? Can that be larger than 1, right? Because it's a probability, right? It's like, for instance, f of x is the probability that x is less than or equal to x. So because it's a probability, it cannot be larger than 1. So this will be false. So far, so good? Okay. All right, so suppose the following failure data follows kind of a Weibull distribution. The corresponding hazard function is decreasing. Okay, how would we start addressing a problem like this? Let's reconvene. Like, what do we know about Weibull and hazard? The value of beta, that's what matters, right? If beta is greater than 1, then it's increasing. If beta is less than 1, it's decreasing. If beta is equal to 1, it's CFR constant. Okay, so we know what we want, and we know how to fit a distribution to a bunch of points, right? So that's what we're going to do. Let's see. Okay, so this is our data. So I want to do what? First, I want to make sure my library is loaded. Okay. So then what do I do? No help? Okay, fit distribution to x and Weibull. All right. I wanted shape. So shape is here 6.68. I don't even need to do, if it was 1 or something, maybe I would need to do a test, make sure that it's actually greater than 1 or not. But then here it's so far so much bigger than 1 that I'm sure that this is increasing failure. Right? So if it's increasing, then this is decreasing, so this is false. Right? And everybody, again, different variations. So you may not have got these numbers with these like formatting, but same kind of concept you were testing. Make sense? Any questions? Right. So let's look at the next one. Okay, similar question, but slightly different. Okay, so now we have another set of data, 10 data points, but we know that now they're following normal. But you're asked the same question. Is hazard increasing or not? Okay, so we want hazard. Let's see. So let's plot hazard. All right, that should be easy enough. Then we can see if it's increasing or decreasing. Right. So I'm going to say, okay, X, this time around, I have these numbers. Okay, so let's fit a normal, get the parameters of normal. Okay, So I get mean and standard deviation back. Then what do I want to do? I want to plot hazard. Hazard is what? Lambda t is equal to ft over rt. Okay, ft over rt. So let's plot it. So I'm gonna use the function, the command curve. So I want ft. So it will be d norm, right, of x with mean is 8.95 and standard deviation is what? 3.11, right? This is ft, fair enough, okay, over rt, right? So rt, what command do I use? Rt. Or p, right? I want reliability. Perfect. P norm of, again, x equal to, sorry, this is giving me a lot of, what did I do wrong? Oh, sorry. Yeah, it's giving a lot of messages trying to help me. Okay, 3.11, right? And then I need the lower tail to be false because I want R. Okay, no problem. Okay, so we are plotting, like look at what we are plotting. They're saying plot for me, right, f, the norm, with the parameters that I got back from fitting a line to it, right, over R, p norm, then lower tail is equal to false. Right? Okay, so let's see. I need to make this bigger. All right. Agreed? This is increasing. So that's it. Okay, so this is the way you could answer this problem. But there is an easier way. What is the easier way? Normal is always increasing failure rate. We had a sentence in the slides. Normal is always IFR. Right? So again, true, false. It doesn't matter how you reach that response. Hopefully not with a coin toss. But if you remember that, like we mentioned that, or you remember that we had plots like this, right, for different values, or you go actually do the work and calculate it and plot things and like look, oh yeah, this is increasing, everything is acceptable, right? But then a lot of these things, they were shortcuts, right? They were something that we had said in class that hopefully had helped to do them a little bit more quickly. Any questions so far? Good. Okay. All right, the next question was essentially something to be looked at in the first few, I would say like 2-3 slides, as 2 or 3 classes. So we have a reliability function, and then I'm asking you for mean and standard deviation. That should be pretty straightforward. How do I get mean and standard deviation? What are the steps? I'm not doing the work here. What are the steps? Okay, what would that give you? Perfect, MTTF. All right, step 1, let's just check. Okay, now I want standard deviation. How do I get standard deviation? So, maybe I can start with variance. How do I get variance of a random variable? Do you remember e of x2 minus e of x to the 2? Okay, so this is essentially this. I already have that, right? Next, I want e of x2. How do I get e of x2? Integral x squared ft x dx. So I need f. How do I get f from R? You remember we looked at how to go from each one of the 4, right? We said there is a relationship between fx, rx, capital Fx, and lambda x. Derivative. Yeah, take the derivative of R. but negative, right? And that will be your F. Plug it in, just use the equations. Make sense? Okay. So then we are going to hazard, right? Again, we knew the relationship between these four, emphasize it multiple times. Okay, now I want lambda. How do I get lambda? We looked at the last slide, fx over rx. So you calculate lambda, then you have a function. You can again plot it, take the derivative to see what's the slope, right? There are a lot of ways to see if the function is increasing, decreasing, whatever. That's f over r. Okay, any questions? The mood is very gloomy. Okay. All right. But then again, now you know at least. You know the pieces. You just need to put them together. Okay, let's look at the next one. All right, the component has a Weibull failure distribution. Shape is given. Characteristic life is given. What is characteristic life? The other name for scale. Okay. So there were a couple of questions on reliability and design life. These should be very straightforward, like P Weibull, Q Weibull, right? So just looking at, yeah, we can use R, you can not use R, whatever. Okay. Then we had a question on by how many days will the design life extended? Will it be extended as a result of a burn-in period, right? And a given burn-in period, and a period was given. This was exactly like one of the questions we looked in class. You remember? Like when we said, oh, you want RT given this like T0 to be equal to like this number, like let's say 0.9 or whatever, right? And you simply write this as RT plus T0 over RT0. And this was exactly the same as the class assignment or something we looked at in class exercise. So hopefully this so far straightforward. Then we had a student question. So anybody, okay, don't admit, you might get in trouble. But that was a good question and I liked it and I put it in the exam. And hopefully the person who wrote it got it right, because that was the whole purpose, that like when you give the question to us, we're gonna use it, you know the answer. So but let's think about it. This was a very good question. So what is the likelihood that 25 out of 50 such components using a test are functional after the given time? And this time, again, I was trying to save time. So this time was exactly the same as this time that for which you had to calculate reliability. So part A, you calculated the probability of failure or success, right? By a certain point in time, right? You just had this in part A. So part A, let's call it R0, right? This was the probability of the reliability, let's say. You calculate that. Now, what does this question say? So it says, okay, you had only one, you calculated reliability up to this point. Now I have 50 of these. What is the likelihood that 25 of them survive beyond this point? Again, we looked at this example in class. What is the random variable that we are interested in this part? Let's verify. Do we know the exact number of trials? Yes, 50. Do we know whether each trial results in failure or success? Yes. Do we know the probability of failure or success? Yes, we got it in part A. Right? Are the trials independent? Yes, because I have 50 components. I'm testing them separately. I'm putting them under test. So what is the random variable of interest? Or criteria? Binomial. Right? Binomial. So you just need to put it in the binomial equation. X is 25, N is 50, and the probability of success or failure is part A. Make sense? Okay. Again, I understand pressure of exam adds to things as well, but like if you follow them right now, if you're comfortable with them right now, that is something. I want you to at least know that, like, now you know, if you were retaking the exam right now you know where to go to find these little pieces to put them together, right? Even that shows that you are learning, right? And that's the ultimate purpose. Okay. All right. Next question. This was, again, very similar to one of the homework assignments, at least the first 2-3 parts, maybe the first 2 parts. Again, we have lambda of the system, lambda of the component. You calculate them. Again, the same steps as homework. But then, okay, this is an exam, so I have to like kind of build on that, add a little bit to it. So this part was supposed to be stretching what you know already based on the material that we had learned in class. Let's see, what is this question? So now by this time we have lambda of the system, lambda of each component. Okay, so what is the probability? And we know that, right? We know because it's constant failure, everything is CFR, right? Which is exponential distribution, right? Okay, so what is the probability of observing 2 or more component failures? So let's draw a diagram. So let's say this is the beginning of the time. This is first failure, second failure, third failure, fourth failure. The times between them are exponentially distributed. So if I want the number of events up to some point t, so systems MTTF, I could say like t equal to 100, whatever it is, right? If I have a t, let's say the same 100. This is not exact number, but let's say it is 100, whatever, right? If I want to count, what is the probability that I have n failures? N equal to n. What is that distribution if the time between events is exponential? What's wrong? Yeah, that's it. So you just put it in Poisson equation. Okay, so it doesn't want exactly 2, it wants 2 or more, which is again very similar to one of the other assignments we looked at. If you want 2, 3, 4, 5, 6, 7, all the way to infinity, right? You go 1 minus whatever it's not there. 1 minus 0 minus 1. And then that would be your answer. So 1 minus Poisson evaluated at 0, 1 minus Poisson evaluated at 1. If you had, so some people had 2 or more, some people had 5 or more, like whatever. Like the same concept. Make sense? Okay. Then we had another question. This was supposed to be very quick. You could calculate it, or you could just write the answer. So let's see. What is the difference between the probabilities of system failure from days 10 to 20, given that the system has survived up to 10, right? And 30 to 40, given that it has survived up to 30. So what is this period? How many days is this period? 10 days. Okay, what is this period? 10 days. Okay, so let's simplify the question. What is the probability that the system survives another 10 days, given that it has survived up to now? Same probability, memoryless property. Right? So you could actually calculate this. Right? You could say pxp of this minus pxp of that over that. So you could do that and you would get the right answer. But this was supposed to testing the concepts that we had learned in class. Right? That exponential forgets. Given that you have survived up to this point, because it's exponential, it forgets, and it just looks in the future. What is the probability that it will last for another 10 days? Yeah, it was the part of this problem where we had constant failure. Yeah. They wouldn't fit in one slide. I had to break them down. Okay. So next one. This setup was again very similar to, I think, last to second last homework 5, first question. Very similar concept. You solve 2 equations, 2 unknown, you get mu and sigma back. All right, that's first step. And then it asks what is the probability that component will last between these 2 times. So I could ask, what's the probability that you fail at this? What's the probability that you fail at this? Subtract. Right, the same thing. So then you get the probability that will last between the 2. Okay. Then it asks for the hazard rate. The same thing we did. You want fx over rx at that x, that's 60. Hazard function. Lambda x is equal to fx over rx. Okay? And then this was also very similar to maybe the student submitted question, right? Because this is 50 components are given, they're tested. How many do you expect to fail? Again, binomial, so this would be E of x equal to MP, right? But again, I was trying to save time. So this probability was exactly the same as the one that you calculated in part A. So you just needed to multiply that probability, whatever you got in part A, by 50. And that would be it. Or like 1 minus that by 50. Because I think one asked for failure, the other one asked for survival. But again, it wasn't supposed to, like, you didn't need to recalculate things. At least you could reuse them to some extent. Okay? Then we said the definition of log normal. Right? It has a log normal distribution whose logarithm has this mu and standard deviation sigma. So essentially you would just call P L norm. Right? And then mu and sigma are given because PL norm exactly needs mean and a standard deviation. You just plug in the two values that you got and then report it up to whatever time that's asked from you. All right. This question seemed to give a lot of people a lot of trouble, but that wasn't the intention. You remember we looked at this so many times in class when I generated random numbers for you. And it was also in the slides. And like whenever we gave D norm, for instance, P norm, Q norm, there was always an R norm or R something. Right? Even if you missed that part when I did that in class, you could just go back to your notes and see, oh, there was a random generator. And like that was a sentence that was given in the slide. So you would just need to call it. Because so many people seem to have missed it, so let's look at it together in class. Make sure that you know how to do it. Okay, so let's generate 1,000 random numbers from exponential with rate 10. So you need to use REXP. I'm generating 1,000, and it gives you hints like n and rate, right? Generate 1,000 with rate 10. Okay, I'm gonna put them in X because I need to do some kind of manipulations. Okay, next it wants to plot the normal probability plot for it. One command, right? We looked at that. One command. What's the command? QQ norm. QQ norm of X. What do you expect? We generated numbers from exponential. If you generate QQ norm, normal probability plot, they will fall on a straight line if they follow normal. This comes from exponential. So highly unlikely that they follow normal. So let's verify. They indeed don't, right? There's no straight line going through these. So it's not normal. Okay. So then it says, oh, see if it's Weibull. Okay, we verified it's not normal. Let's check if it's Weibull. You should already know what the answer is, right? But then let's verify. So first I want to fit a Weibull, right? I've done it here before. So let's fit Weibull. Not normal. Weibull. Okay. So I fit Weibull, I get shape and I get a scale back. Look at shape. Shape is almost 1. All right, so that should already say something to you. Shape is equal to 1. Weibull converges to CFR, like to exponential. Okay, let's verify again. Okay, so all right. So now I want to conduct a test. I do a KS test. There I am using X, P Weibull. Okay, and then I get the shape. What's the value of the shape I should use? You can read the screen. 1.04. Agreed. That's the number I got back, and everybody gets different numbers back. It's okay. You're graded based on your work. And then scale is 0.10. okay, I get a p-value that is very large compared to like 5% or 1% or whatever, right? So I have no evidence of rejecting that this is not viable, shape 1, which makes sense, right? Because exponential, I generated from exponential, viable with shape 1 is essentially exponential. So that makes sense. So you had some hints going in, what do you expect to see? And then we verified it with the work that we did. So, okay, having seen all of these, what do you think about final? Oh, like, sorry, about the midterm exam. Okay. But that's a very good observation though, because now you know where things are, or like how you should have consolidated everything into the exam. But hopefully, like, you saw that nothing was out of place. Everything was based off of the material that you'd seen before. But the other thing you know is now you know how to study for the final. This is the way things are. You're going to be questions on things. You cannot expect, because again, it's open note, open books. You cannot expect it's going to be exactly the same thing as you've seen in homework, but it's a combination of things that you've seen throughout the course. Agreed? Fine. Okay, I can give you a closed book, closed notes exam, but I don't think anybody wants that. Am I right? Okay. So we're going to keep the same format, but try to study as if it's closed book, closed notes. Right? Come prepared. Know where things are. And again, you have them at your disposal. The other thing that it may help is to essentially write a story of the class, right? Or like write some kind of like a reference point. Like in these lectures, we looked at this. In these slides, we looked at that. Something that you can kind of like a reference or like a dictionary, right? You can just refer back to the notes. So come up with the strategies. I think like we're engineers, we like puzzles. So come up with a strategy of how you would have approached this midterm exam if you had a chance to take it again to succeed, and then try to use that strategy on the final exam because it's going to have the same format. So hopefully that will help. Okay, so we are going to have our final exam, which is going to be comprehensive, covering everything. So more material, right? More things to make, like to know where things, like you need to know where things are, but like more material. But again, you have everything with you. December 6th. This is different from what is put on the website. I verified we have this very same room. If you're a distance student, you're welcome to come to class again. We have like 3 big rooms reserved, so we can seat everyone. So come early. We're going to start at 5:05. And if you're a distance student, you cannot come to campus to take the exam. Please follow the same instructions that were given on Canvas. If you're using the same proctor, it's okay. Just email us again with the same title so that we know, and like we're gonna send the exams to your proctors at the given time. Please let us know by Monday, November 26th. Okay. All right, let us start with new topics. Reliability block diagrams. Okay, so far we've looked at mostly one system, right? We said, oh, this system has Weibull distribution. This system has normal distribution. This one is distributed according, time to failure is exponential, right? We looked at individual components or systems as a whole, but like one component, right? But most systems are made of a lot of components, right? Now we want to know if we have an array of components put together as part of the system, and we know the reliability of each component because we've learned in the first half of the class, how we are going to combine them to figure out the reliability of the entire system. So first half was component level kind of concentration, and second half is system level. We are scaling up. Okay, so we're going to use reliability block diagrams. The name may sound fancy, it's very simple. So we can have series model, parallel model, a combination of parallel and series, and like complex models. Okay, so let's start very, very simple. So series configuration. So let's start. We have 3 components, A, B, C, and then they are serially related, and they are independent of each other. So when I say serially dependent, right, or serially related, it means that they are kind of in line, either physically or the way they work. And it means that if one of them fails, it breaks the link between input to output, so to speak, and the whole system stops functioning. So if A fails, the system stops functioning. If B fails, the system stops functioning. If C fails, the system stops functioning. Okay. So if I want a system like this to be reliable up to, let's say, T0, what do I know or what do I need about individual components by time T0? All of them need to be reliable by that time. So the probability that, let's say, component 1, TA, time to failure for component 1, that should be greater than T0. And time to failure for component 2 should be greater than T0. And 3 be greater than or equal to 0. Right? That is the only case where my entire system remains reliable up to time T0. Fair enough? Okay. So we know that they're independent, or we assume they're independent, which means what? Okay. But what does that mean if I have probability and I'm using and between the three events? Multiply. So I can write this as probability that TA is greater than T times the probability that TB is greater than T times the probability that TC is greater than T0. Right? Each individual one, the time to failure for them should be greater than T0. What is this? This is essentially the short form for that is RA T0, right? Component A needs to be reliable times component B needs to be reliable by that point, and component C needs to be reliable by that point. That's it. So if you have a series system, right, or components are serially related to each other, then reliability of the system is essentially the multiplication of the reliability of the individual components by that time. That's it. Make sense? Okay, so let's generalize this. So if you have a set of serially related components and you have R1 through Rn, right, for the components, then reliability of the system is just a multiplication of individual reliability up to that point. Okay, we all know that reliability is dependent on time, right? But in this part of the class, sometimes we may use the simpler notation, remove time, because we all know that time is there. So it's okay to use the lower one, even though it's more proper to use the red one because it has the time explicitly mentioned. All right. Any questions? Okay, so if that's the case, let's go through this. So you see, we have three components here. Two of them have a particular rate of failure, which is constant. And the last one is Weibull distributed. So that's why the final exam is going to be comprehensive, because we cannot know anything about the system without kind of knowing about the components. So you have to like kind of know everything about components and then scale it up to a system. All right, let's work on this. And let me know if you have any questions. I'm going to walk you. All right. A lot of you got it right there. All right, let's look at it. Okay, so the third one is Weibull. Let's first knock that out. So P Weibull. What do I want? So let's do it like this. We know the shape. Shape is 1.5. We know the scale. That is 37.5. And we know we want reliability, so I'm gonna go lower tail equal to false. Okay, so I know that the components are serially dependent, right? Which means that if I get the reliability of each of the components and then multiply them all, I get the reliability of the system, right? So when do I want the reliability of the system? Up to what point? 75. So I'm gonna do the same thing for components, right? So I'm gonna get the reliability up to 75. So okay, that's the first one down. Make sense? Good. Okay. So next one, components A and B have one number, right? And that's it. Like this is these many failures per hour, which means that the rate of failures is a constant. When I say constant failure rate, the first thing that should pop into your head is exponential, right? CFR exponential. So okay, exponential. PEXP. Again, at the same 75 hours, the rate is what's given, right? Failure per hour, that's the rate. So my rate is 0.0002. And don't forget that you want the reliability up to that point. So lower tail false. So one is this one, and the other one is very similar, but for 5. Okay, so you got 3 numbers, just multiply them. That's it. Fair enough? So you see how I can test you like part A, right? Let's think about like, I haven't written the final yet, but like that's how I would approach it, right? Okay, I want to test them on their knowledge on components, on lifetime distributions of components, and then I want to test them on their ability to put this in a system, right? Put them together into a system. So maybe first part is, what is the reliability up to 75 if I have Weibull? What's the reliability if it's P normal, log normal, right? What's the reliability of whatever? Like we go through that, and then I'll ask you what is the reliability of the entire system. Something like this, I would imagine. Right? So make sure you can go from component to system. All right. Okay. So next, this one is very quick. Let's read through it. And then just shout out to how you would approach it. Very similar to the last one, but easier. Just multiply 3. Okay. So I want R of system 0.9 times 0.999 times 0.95. Okay, that obviously wasn't the purpose of the question because it's too simple. Okay, so did anybody multiply these? Can somebody multiply these numbers and tell me what they get? Zero 0.854. Okay. I want you to observe. Look at the 3 components. Their reliability up to this point, whatever it is, 5,000 hours. Look at the system. Compare the numbers. Which one is the smallest number here? The first one is the smallest out of the components. But then compare that with the system. You see how the reliability system decreased? So you have look at the 3 components. They're very reliable. Like one is 0.999, like whatever, right? It's very, very high. So highly reliable components. When they are serially dependent, the reliability of the system is not that high. So that's not very pleasant, right? We've worked on like improving the reliability of individual components, put them in a system. The reliability of the system is kind of low, right? That is where we use redundancy, right? We go with parallel configurations if we need a higher reliability. Because if we have highly reliable components and we just put them in a serially dependent way, we may not achieve the needed reliability of the entire system. So we need to think about some other approaches. So redundancies work when we put things in parallel. The other word for this is hot standby. So they're both A and B are now engaged, right? They're both working, right? But then if one of them fails, the system continues functioning with the other one. The load will completely go to the other one. So you can think of kind of like different ways that the system can function, right? If both of them are reliable, the system is going to function. If A is working, B is not working, the system is going to function. If B is working, A is not working, the system is going to function. Right? So there are more paths from input to output. And then this is going to increase the reliability. Okay, so let's look at an example. Two components, they're in parallel, 0.95 and 0.9. Okay, let's calculate the reliability of this system and see what the reliability is. So we said maybe one works, the other one doesn't. Right? The top one works, the bottom one doesn't. Right? The top one works 0.95, the bottom one doesn't, 1 minus 0.9. Or the bottom one works, the top one doesn't. Or they both work. Okay, alternatively, how could I maybe do the same thing but a little bit more quickly? With only one calculation. Multiply the two what? I think you're right, but like, let's check because I do it in my head a little bit differently. But I think you're right. So what if I go 1 minus, they both fail? You're right. 1 minus, they both fail, right? 1 minus, this fails, and this fails. Right? Because that is the only way, so it's using complements. The complement of both failing. In that case, the system is working. Right? Make sense? So that's what you're going to do. We're going to say if we have n parallel and independent components, the system is functional if at least one of the components doesn't fail. So in other words, the system reliability is probability of the complement of an event that all n components fail. Right? 1 minus everything is failed, the system is functional. Fair enough? So if I want to write the math, it will be 1 minus the multiplication of 1 minus RIs. Good? Okay, if it's good, let's look at an example. I'll let you work on this one. That's what exactly I saw most of you did. All right, all of you, right? But then, what did you get? 0.9999, right? 325. So compare this with all of these numbers. See how much higher it is? So with serially dependent, we got ultimately a lower system reliability. With parallel, we got ultimately higher system reliability. So that's how it helps. Okay. So you can always put things together, combine serial and parallel, right? And that's the beauty of it. So if you find that like one of your components, you're going to spend so much more to increase the reliability of that particular component, right? Maybe like 5% by 5%, by 10% or whatever. You can essentially think about if, for instance, you can put a couple of those components in parallel, right? And then that way you can kind of increase the reliability of that functionality. And then you can also have the rest of the system kind of related to that component. Okay, so let's work through this one. This is like a little bit more maybe complex, but hopefully simple enough. So here again, as you see, we are failure rate, failure per hour, and we're interested in the reliability up to some points in time. So this means these are exponential. You need to find the reliability first, right? And then kind of think about how you're going to put together two processors together, but then for your system to function, it should have RAM, hard disk, power supply, and monitor. Right? All of these need to be reliable. But then instead of one, you have two processors in parallel. You're combining parallel and series them. That's what I do. And like when we get to something bigger later, yeah, exactly. Yeah. So sort of for drawing the block diagram. So this is the first step. Like you're gonna get more and more like you're gonna go through like more and more complicated systems. So the first step of like creating something like this is translating to an image. Right? We're gonna have your and the series will be monitored, and then the series with two processors in parallel. Okay, so now you have a system, then you can start to supply. If you have things in parallel, you want minus 11. It's very simple. But then, no, not for the red. Hold on. Draw your block diagram for the system. And then that's there. So, excellent. Okay, so let's solve. So for the series one, everything is one divided. Right? So let's look at it from the end. We want this divided to 4. Have it. So, okay, so, I see. So reliability, that's good, reliability, right? So this is, and then in quantity, you want this, right? The palette. Okay, and then this is, if you are doing, so let's see, it will be 1 minus the reliability. Let's see. No. Let me check. Remember that last time. I think you were right before. Tell me on this. 1 minus. Yeah, this is correct now. You know what? Because in this quantity, you have 1 minus, because it makes it, yeah, say here. So it will be the reliability of that times the reliability of that times the, right? So you could do true here, or you could do 1 minus reliability to the 2. There. Yeah. Okay. Well, then you got what I got. What if you something wrong? Up to 1,000 hours. Uh, 2.4 zeros and then 5 zeros. Some they're different. The last two, no, they're both 4 zeros. Hmm. Yeah, my numbers are not exactly as yours, so something is kind of off, but I don't know what exactly. But you're on the right track. But can you check? Can you get this part? Copy that and run this one. You can just run it. Yeah, you can do it. So that's one. Yeah, that's one. Okay, so don't shorten it. Go toward K equals to false, toward K equals to. You have assigned apparently some values to P and F. It's messing up with your equation. So I think that's what happens. If it's just P and F, say lowercase equal to, then it will copy that. You know? Oh wow. The trick is the one at a time. Yeah, but if you stick with the other one, so there are two, yeah, I think that's that one around. Okay, that's good. Okay, I keep forgetting numbers, but your number is too small compared to my number. So something you no, you want reliability, so you have no that's so alright, let's take whatever the other I'll come back to this. Alright, let's make sure we get through this example. Somehow we had a problem with one exercise. So let's see what you guys got. Um, so let's see. We have let's I would always start with drawing a block diagram, right? We have 4 components. We have one of them each. This, and this. And then we have 2 processors, right, that are in parallel, right? We want the entire system to work. For the entire system to work, right, we need to set them up like this, right? Okay, so the reliability of each one is easy to get. So I think this one is point, if I'm going by order, 0.99, 0.99, 0.996, 0.967, right? I multiply, then I have this series, this parallel system. So it will be 1 minus 0.962 to the 2, and multiplying this by the rest. Make sense? And then you would get 0.9426. Right, fair enough. Okay, good. So this is exactly what we did, right? We looked at these two, we collapsed them into a new, essentially, component, and then everything was in series, and we solved the problem. So if we get a complex system, a combined parallel series system, how are we going to approach a system like this? We're going to analyze AC together, like a new AC, maybe a new BB, and then the 2 are in parallel, right? So I'm going to combine these 2, let's say in component 1, combine these 2 in component 2, right? 1 is going to have RA times RC. 2 is going to have RB times RD. Right? And then reliability of the system is going to be 1 minus, let's say R1 times 1 minus R2. Right? Let's say this is R1, R2. Does that make sense? You go through a system while looking at kind of collapsing things, reducing the number of components, kind of combining them based on like series and parallel concepts we learn. And then that way you can analyze a very complex system. So next class, we're going to start by analyzing this system. So for now, let's take a 10-minute break and come back at 6:30 for our speaker. All right. Thank you. Hi. How are you? Very nice to see you. Yes, I am. Thank you so much for making the time. Oh, I appreciate that you're coming to give a lecture from the class. I have loaded everything. Yeah, these are all of the slides, and I've also loaded that's in the OE field. I've loaded this as well,
Good,
so
good.
we can do that.
Okay, great.
And these are the slides. I can open them, or you can open them on demand. Which one do you prefer? Do you want me to open all of them?
Let me get my glasses. Yeah.
Sure.
So we're going to do the first fault tree. I'm just kind of going.
Yeah, yeah. And then the other one, yeah,
They'll do that.
I'll do the other one. And I already have the homework and everything I've shared with you before. You know. So if we can maybe start with like root cause first, and then go to fault tree.
Yeah. So there's a PowerPoint.
Yeah, they're all here. Yeah. Oh, this is like the.
That's an art.
I shared with them. So yeah, I can. Like this. Also, the back one that we get all the
Yeah. So that's PowerPoint. Okay. Good.
So should I close the other ones, or do you want to speak about that?
Let me just spend a little.
Sure. Absolutely. Yes. Yes.
Here, this young man.
Sure. Yeah. Thank you so much. Let me get that. You want water? Oh, you have water. Okay.
I forgot. You can make marks on here.
Sure.
How do you erase?
Oh. Just go over that. There we go.
It's gone. Okay. Good.
All right. So the only other thing is you have to, so you need to clearly allow them.
Okay. Is there? I can walk around.
Absolutely. Yeah, you can walk around.
It's not on. I think I was on the camera.
Yes, actually, they see this screen.
Oh, they said they don't
Yeah,
see me.
and there is a camera too, but then we use that as a backup. So we typically
Okay.
post just voice over PowerPoint.
Okay. Let's see. Why did it stop? Oh, there it is. Okay. No problem.
I'll let you explain a
That is
little
good.
more. There was a student had a question earlier.
Okay.
That's true. That's true. It's just my slides. Yeah, on my notes.
Those buildings are gone.
Yeah,
Look at that church.
yeah. They're gonna become the new nuclear engineering building.
Oh,
It's gonna be like a big complex, like yeah, finished hopefully like I guess 2020.
look like this one.
Bigger. It's gonna be bigger. Yeah, yeah. And afterwards, I think
No
you're
reactor.
hopefully not too close to
Yeah.
our building.
No creek.
Yeah. Farther the better. But then even after that, I think they have like secured funding or something for redoing the side of the stadium.
Oh.
That's the next project. Yeah. So like they had
They need a better football team first.
They won
Then
Auburn.
fix it. They beat Auburn. That was
They beat
good.
Auburn.
That was
so that
great.
was yeah.
I picked up my friend at the airport. He's Alabama fan.
Oh,
So we're going to the game.
wow. Good luck. So hopefully with
We'll
all
see.
the like new blood
Energy.
like, the
Yeah.
energy, yeah.
Yeah, maybe.
Yeah, and like mostly also like is a lot of like mental kind of like
A lot of, yeah.
hopefully can never know. I going into the Auburn game, I didn't think they can do that, but then I think they surprised everyone.
Yeah.
That's great.
You still live in downtown?
Yeah. And we have actually a student in class. He's not here today. Maybe he's practicing, but we have a student who is in football field.
Oh, really?
In our class, yeah. Like we had exam last week, so he was like, "Oh, I have to miss it because we are traveling and so on." I was like, "That's okay, you can take it later." But then, like, they won.
You know, there was 2 students from last year who went to work for Schlumberger. You know, that's a big oil drilling company. They called me. I did this same thing as a webinar for
Oh,
Schlumberger.
fantastic! That's awesome. Yeah. Make sure you mention it to them because I think it's pretty cool.
It was cool.
Yeah, bring it up to them. Maybe like they also like go to a new company and like to get some workshops or
Right.
something.
I mean, they had a seminar program, so I did it completely remotely.
Yeah.
Webinar.
Awesome.
But
Cool.
thank you.
I mean, it's a very good lecture.
Thank you.
Honestly,
Yeah.
I love it, and like they always like seem to like really enjoy this class. Like
Good.
because yeah, I love it. All right, so I guess we can start. So do you mind giving a little like background about the job?
No. So,
I think it's
the clip, okay?
I don't think it's clips though, but
Oh,
inside.
okay.
Then
Try.
it's loud.
Okay.
Yeah, I want to make sure that you can see that also.
It shows up on the. Is that okay?
I think
You
it's
think?
okay. Yeah.
Okay.
It's fine.
All right. Good.
All right. So finish.
Okay. Hey, everybody. How you doing? Very good. All right. My name is John Farquharson. Don't worry about pronouncing my last name. Anybody remember Shrek? Lord Farquhar. I'm his son, Farquhar's son. So it's a good Scottish name. I had the opportunity this summer to go back to Scotland and saw my family castle. There is a Farquharson castle over there. So bucket list. There we go. So I click through the slides just like this. So just a little bit about myself. I work for a company called ABS, American Bureau of Shipping, and we have an office out on Pellissippi Parkway, Knoxville, and our main office is in Houston, Texas. That's our company headquarters. We've got offices all over the world. Later this year, I get the opportunity to go to Saudi Arabia for 2 weeks to teach courses. So I've never been to that part of the world, kind of looking forward to it. But we go and do analysis for facilities that have chemicals, nuclear facilities, pharmaceuticals, anything that has risk associated with it. So a lot of the techniques that you guys are learning in these courses, we do them full-time for companies. So what we're going to talk about today is root cause analysis. There's a handbook that our company developed, root cause analysis handbook. And so some of what we do today is going to come straight from this book. So I'm going to be referring to that some. So, okay, there's my information. Feel free to give me a call, contact me. One thing a little interesting, I've done this 3 years now. And last year there were 2 individuals who actually went out and got jobs. That's something, isn't it? That you can get jobs after this and make money. But they called me and said, hey, would you do a webinar of this for our company? It was Schlumberger. It's a big oil drilling company that's all over the world. So anyway, just keep that in mind. If you ever need anything, I am a University of Tennessee graduate, so I feel like it's my duty to help you guys. So whatever you guys need, I can help you. Yes. Yeah. The university needs money. Not just the football program needs money, right? We got to build these. We're going to get better football team. It's coming. So hang in there. So what do? We do a lot of things in a lot of different industries. I mentioned some of the industries: manufacturing, chemical process. Most of the work I do lately seems like it's for the chemical industry or oil refineries. So we've authored a lot of books. There's an organization called American Institute of Chemical Engineers, and they have an organization within them called the Center for Chemical Process Safety. So a lot of the books and publications that we do are for that organization. So that's what we do. We write a lot of books, do a lot of analysis. Talking about root cause analysis, what does that really mean? Something bad happened at your plant, at your facility. They may call somebody like us to come in and kind of say what exactly went wrong. We're trying to get at what the root cause are, but in order to get there, we have to go through and say, all right, what was the equipment that failed? What was the frontline personnel failure that occurred? Why did that happen? And kind of work through. So I'm going to show you just a little bit of those techniques tonight. So yeah, there's a lot involved with running a project. As a team leader, you got to worry about incidents. You got to be worried about documents, lots of different things. Yes, occasionally we get involved with lawyers. So, you know, everybody makes fun of lawyers till you need one, and then they're your best friend. So, what type of work do we do? You look at our consulting type services. You can divide it up into things like risk planning, operational support, and asset integrity bundled services, we call. Most of what we're going to be talking about today, I think we could zero in on environmental health and safety. Most of the incidents that we're concerned with are typically safety events or environmental type events. So when you hit that, you got to do that. Where are we? We're all over the world. We've got, as I said, I'm going to this part of the world later in the year, a race. You told me exactly where a race was. Up there. Thank you. So I'm going to erase all that. And be careful, because when it marks, it goes over to the next slide. I didn't realize that. Okay. Okay, no problem. So our headquarters in Houston, Texas. Thank you. And you notice a lot of places where we have offices are kind of where the oil is. A lot of the work that we do is for the oil and chemical industries, and so that's where, and shipping, obviously, because a lot of what we do is to help regulate the shipping. All right. Incident investigation. Let's talk a little bit about that. What do we mean by root cause? And anybody ever hear that term before? See a few heads nod it. Yeah? Okay. We've been doing it for a long time. And so you can think of it as a systematic method, investigate an incident or series of incidents. And so usually it's not just one thing happened, but crap, we had a whole series of these events that have happened. A lot of times it's for safety. A lot of times it's for quality. Any quality control people, is that something that you kind of specialize in industrial engineering? So when we do work for pharmaceutical companies who have regulated by the FDA, then they're very much concerned about quality incidents. So sometimes it's that, sometimes it's safety. We want to understand the underlying causes of the incident. Why did it cause? How do we work that down to our management system issues? A lot of times it's not, we just blame the operator. Well, perhaps we set up the operator in a way where he was set up to be for failure. We try to make it as good as we can to try to minimize human errors. And then corrective actions. What can we do to make it better? What can we do to prevent this incident from happening again? A lot of times it's looking at the management system. What can we do to improve the management system? So we have this triangle. We work down. We start at the top where we have equipment performance gaps and frontline personnel performance gaps. So what we're looking at typically is the guy or gal who's out in the field has a hands on the equipment. That's what we mean by frontline personnel. Could be operating people, could be maintenance type people making the error. What happens? That could be because of task control issues. You kind of think of that as the procedures. What do you have in place to do your job? It may be process control issues. Working your way down, we're getting to management systems issues that are eventually oriented and caused by the culture of the organization, organizational control issues. That's where we're trying to get to. So as far as dividing it up into the different areas, we would say the field personnel would be at the top. Then there's support groups, maybe maintenance support groups, procedure writing groups, that sort of thing. And then down at the bottom is, of course, the management. So that's what we're trying to get to. So here's a term for you. Causal factor, not casual factor, but causal factors. That is identifying what really went wrong. What was the event? What was it that contributed to the event as far as looking at the frontline personnel and looking at your equipment? Start with that. Work our way down through what we call intermediate causes. What was the cause of this causal event? And then working down in even more detail, what are we getting to the root causes? What are the management issues that are there? And so what we do as engineers, we make up charts. And so we have a nice little thing called a root cause map, where if you look at, and I'm sorry, I don't have a slide on this, but if you look at different types of issues, and then you can break it down into different areas, maybe as a supervisoral issue, human factors issue, might be a procedural issue. So, and this is just a way of going through and categorizing what the different root causes could be. So I'm just going to let y'all pass this around, look at it as much. I believe we can have that on the website. I think you guys can download that, I believe. So anyway, that's what we're trying to get to. We're trying to get at the root causes. How do we start with causal factors, work our way down? Why do we do this? What's the benefits of it? So it's very easy to sit up at the top and say, well, Fred, the operator, forgot to open the valve. That's exactly why this happened. We're going to fire Fred. Does that solve the issue? Maybe, maybe not. Probably not. You know, it could be that we asked Fred to open up this valve 365 days a year, And if he didn't do it, the chemical reactor would immediately blow up. Well, we're setting somebody up for failure when we do that. Think about human factors. Think about making mistakes. I assume most all of you are drivers. Many of you have driver's license. Who here has just brain dead driven through a red light? Yeah? Okay. A lot of you are liars because you haven't done that. But anyway, so I've thought about this because, you just wake up and, whew, that was a red light. And luckily, we're here to say we didn't get killed. Maybe there was a fender bender or something because of that. So I started thinking, what is the probability of failure? How often when a human is given a very important task, stopping at the red light, and he just goes right through the red light? So what I did is I did a little calculation. I live out in Oak Ridge. I work in Knoxville. And so I said, well, there's about 10 red lights in between my home and work, and how many days a year do I really work, and blah, blah, blah. I went through the calculation, and I said, well, about once every 3 years, I just go crazy and run through a red light. Luckily, I haven't been run over yet. So I go through the calculation. How many opportunities did I have? Back out a calculation, I came up with a number of 3 per 10,000. That's a pretty good number. You think about, but you have so many opportunities to make that error that it is, could be a fatal error. So, but to help my research, the city of Oak Ridge implemented a program where they had a red light that if I ran through that red light, they would send me something in the mail, and for only $50, I'd get a picture of me going through the red light. But now most places have done away with that. I don't know if there's still some in Knoxville, maybe. I don't know. Always look for the camera when you do that. So yes, human errors are out there, and we do everything we can to minimize that. So we're starting a structural analysis. We start at the top and work our way down. As we go down, we're going to have a more detailed analysis. We're going to learn why this happened, and we have an increasing scope of corrective action, such that we look at why did Fred not open the valve? Maybe we can focus in on our tire facility. What other type of operations are that were out there that we are relying on our operations people to do? We're setting them up for failure, like me driving through the red light. So the best way to learn anything is to do it. So what I'm going to do, I'm going to start a video, and we're going to show a certain portion of the video. And then what I'm going to ask you to do is to write down on your computer or whatever, write down what you think the causal factors, root cause, and recommendations. And I don't mind if you work in pairs, work in groups, so that we're going to show the video, and then once we get to a certain place, we'll stop it and let you write down what you think causal factors, root causes, recommendations are. Yeah, I don't think it. No, just I don't think it. Okay, good. Okay. You guys hear that okay? Okay. So would like for you guys to do is to sit down, as I say, in groups or by yourself and write down what you think the causal factors are. What was the frontline personnel performance gaps or equipment performance gaps? And for each of those, think about what was the root cause, or what do you think the root cause of those performance gaps were? And can you come up with any recommendations, any corrective action? I'll be walking around. If you have any questions, just holler at me. We'll spend 10 minutes or so on this. Wasn't much oversight, was there? They were told, get out there, get this done. Yeah, it didn't seem like there was much guidance. Do you really? What part of Mississippi are you from? I've been to Port Gibson and Vicksburg. I was amazed. I drove through Mississippi. How many oil fields are out there? Yeah, you wouldn't think of it. Yeah. Uh-huh. Yeah, it is, this chemical safety board, there's a lot of interesting videos on how accidents occur. So, well, good. Exactly. Yeah, right. What's that? Yeah, yeah, I think so. Engaged. I mean, student. Yeah, that's a big class. Every year? Is that it? Ah, yeah. Reliability? Mm-hmm. Where's the nuclear department while they're doing the construction? Mm. I was in Dougherty Hall, and mechanical's still there, right? Yeah. They had a lab in the basement where they do stress strain. I worked with Dr. Speckart, you remember? Oh, he was great. He was a good professor. He passed away now. Yeah. How long have we done it? Okay, no, I mean, when did I start? No, I mean, let me. So, how's everybody doing? Did you come up with some causal factors? What would be one causal factor? Anybody? Causal factor being a frontline performance gap, frontline personnel performance gap. What did they do wrong? Yes, sir. They didn't sample the air in the working area. Yes, ma'am. What else? You didn't like that? Two people standing on a ladder to hold. Yeah. Anything else? So they didn't check. They didn't do a good job checking it. The whole thing about, although, you know, they did hold the guy in place until, but they were putting what? Extra personnel at risk. Yes, sir. Exactly. Yeah. Why were they there? And why didn't they have safety harnesses on? So what that is a lot of the causal factors. Any equipment failure? I mean, everything worked the way it was supposed to work. Is just the people didn't do what they were supposed to do. Okay, so that's causal factors. Root causes. What do you think? Why did they do this? Cost? I'm sorry? Yeah? Poor training, maybe. No oversight. Yeah, who was in charge? Right. So you get the idea. So that's root causes, corrective action. What do you think should be done here? Implement better training. Standard, any operating procedures. We didn't know, I never heard about any operating procedures. Safety over deadline. Yes, sir. What's that? They didn't check, make sure the tank was empty. They, yeah, how about that? Is that a good way to check? Apparently not. No. Yeah. It's like me checking my gas grill by putting a light down. I wonder if this is turned on. No. Anyway, so a lot went wrong here. And that's what a lot of events are, incidents. It's not just one thing. It may be a combination of things. They just ended up in a bad day. Oh, I forgot to mention, Chemical Safety Board is a government agency. They have about 100 people. They're located in Washington, D.C. Their job is to go investigate events. And it's really a great place to work. I've done some work for them there, and they do about 12 investigations a year. And so they really, all they can do is make recommendations to OSHA, to EPA, to local agencies, to engineering associations. So anyway, what I'll do is play the rest of the video, and we'll see how close you guys got to what the Chemical Safety Board said. Just that okay? Yeah. Okay. Okay. All right. Okay. So if you get a chance, you might want to look at that website. There's a lot of interesting videos. It's funny. I teach a lot of classes. Some of them aimed towards the chemical industry, some aimed at the nuclear industry. And I end up showing videos from the chemical industry. And people ask, why don't you show more videos from the nuclear industry? Well, thank goodness there aren't that many accidents. I mean, of course, what happened in Japan and Chernobyl, and they do occur, but not like in the chemical industry. So let's go back to where we were. So was that one of the, okay. Great. Okay. So you guys kind of get an idea. This is kind of like the final product of a root cause analysis, coming up with, hey, here's your root causes. Hey, here's some recommendations to make it better. So how do we get to that point? Well, let's talk some more about that. Activities that an organization needs to function well. So we do different types of analysis. This is more of a looking back analysis. This event happened. Why did it happen? What happens a lot for nuclear industry and chemical industry as well, we do proactive analysis of potential problems. They do something called a process hazard analysis of a chemical system to say what potentially could happen here if you mix chemical X and chemical Y. So that sort of thing You do proactive. Integrated management system that covers all activities. So that risk management is a big deal nowadays. So these companies that have hazardous operations, it's very important that they look at everything that they do and try to take an integrated approach on how we can do it safer. What we're going to talk about tonight is looking at problems using root cause analysis, incident investigation, kind of a looking back type analysis. How they relate, they're kind of all tied together. I know this is an eye chart, you guys can't read it, but proactive management systems, reactive analysis. You kind of have to do all of that, especially the proactive. Probably most of the work I do is more proactive, looking at systems, looking at facilities, what potentially could go wrong, what's in place now, what do they need to do to improve it. So let's go through another example. This is an example of a machine. So that our first thing happens, the machine shuts down. Why? Well, there was a bearing on an exhaust fan that failed. Why? Well, the bearing wore out. Why? The bearing was not replaced in accordance with vendor recommendations. They were trying to save money, or they just fell down on far as a preventive maintenance programs, like not changing the oil in your car. You go 20,000 miles and not change the oil in your car, guess what? You might have an engine failure. Why? The bearing replacement was not scheduled in accordance with the recommendations. Turns out that they didn't have, they had inappropriate procedures. They were incorrect. They didn't have the right information in there. The frequency wasn't specified. And this isn't the only fan that they had problems with. They had a lot of preventive maintenance plans they had issues with. Program wasn't set up. So again, you work all the way back and you find out that there's something called the root cause, and it was that the procedures were not in place, procedures were not enforced. That's what we're trying to get at. Terminology. Incident is typically has a consequence associated with it. A near miss is something that occurs, we didn't have a consequence. It's like me running through the red light and I didn't get hit by a red truck. So, just lucky that time. Causal factors, again, frontline personnel, equipment performance gaps, and intermediate cause as you work down the triangle to try to get at what the root cause is. Items of note, it may be that while we're doing our root cause analysis, we run into something else that's interesting, we note it, it didn't necessarily contribute to the event. So here's our definition of incident. Unplanned sequence of actions, conditions could have resulted in unacceptable consequence for the stakeholders. And so we're saying here, incidents can include both accidents and near misses. It's enough to get management's attention to say, hey, we need to do a root cause analysis of that. That's what they'll call an incident. Near miss, an incident with no consequence that could have reasonably resulted in consequence. We got lucky. It's just no one was in the room. There wasn't a truck coming the other way. An incident that had some consequence that could have reasonably resulted in much more severe consequence. You have perhaps a first aid injury that could have easily resulted in a more serious injury or a death. So that's the kinds of things that we're trying to look at. Causal factors, again, at the top, performance gaps. We've talked enough about that. Equipment performance gaps, the machine broke, the bearing failed, whatever that might be. Frontline personnel, the guy didn't turn the valve in the right position. The guy didn't follow the procedures or yeah. Intermediate cause, working our way down, perhaps they didn't have the procedures. Perhaps they didn't have the right equipment. Perhaps they were put in a situation that was difficult for them to operate. So I'll tell the story. When I went to Scotland, we rented a car. My buddy, the Alabama fan, who I got to go meet at the hotel later, He was in the, and of course I'm sitting on the right side driving. Anybody here from a country that drives on the left side of the road? Okay, so you know. Does your car have, is it right side drive? Yeah, okay. Confused the heck out of me. The feet are the same, but I'm using my left hand to change the gears because it was a manual transmission, which I'm not used to. And they had these low profile tires. And so rented this in downtown Edinburgh. And the first thing we have to do is pull out in traffic and the roundabouts. It's a big deal. And you're going backwards on the roundabout and I'm changing gears and there's a big curb. And my friend James says, curb, curb, curb. Boom, boom, boom. What do? I hit the curb. And it scratches up 2 tires that the rental car company and I are still fighting about. So I was in a situation completely out of my element, had 0 training. All you need is a driver's license and a credit card, and you'd be 25 years old, and they'll rent you a car most anywhere in the world. So I feel for these people that are in situations where they're set up for failure. I feel like that was the case. Last week I was at Bahamas and it was much better because the steering wheel was on the left-hand side. I don't know why. And it was an automatic transmission. So it did something to improve. And Bahamas is not quite as crowded, overwhelming as Scotland, although there's crazy drivers everywhere. Anyway, long story, trying to get at the intermediate cause, trying to get at the root cause. Root cause is where we earn our money by coming up with ways to improve the system. So maybe for a causal factor, there could be as many as 1 to 4 root causes. The maps made it all the way almost to the back there. So you see, there's a whole thing of root causes you can pick from. We'll kind of give you a little structure to go through. Items of note. Hey, we discovered something else. Audit findings. Hey, besides this issue going on at the facility where they weren't following procedures, there's also some other things going on where they're not doing good housekeeping. Didn't necessarily lead to the accident, but it's something that they ought to straighten out. So you just make note of that. Maybe there's a different incident that could occur. That's what we're trying to get at. Management systems, what is the carrot that they use to improve systems? So, and we do work with a lot of different chemical companies. And there's a few, and it used to be Dow and DuPont, I think they're together now. There's a few companies that are really at the top, they do everything right. And then I've been at other facilities where I think I can't wait to get out of here, where they have, near misses and, oh, don't worry, John, it was just a small release. And as long as you stay inside, you'll be okay. And then there's a whole group of companies that are kind of in the middle. So it's a culture. It's a culture. What's more important, getting the product done or getting people home safely? And I think somebody noted that in that incident, they probably were told, you go out there, you weld that pipe in there, you get this done today. We got to get it done today. So those guys were under the stress of getting it done, more important than the safety. So hopefully that is kind of changing. Key points to remember. Reactive analysis, feedback on the performance of management systems. That's what we're trying to get at. Management systems, informants the performance of people or equipment. People put in situations where the carrot's out there. If you improve productivity, then that's what they're going to work towards doing versus improving safety. Our goal is to ensure that the proper safeguards are in place. We need to achieve this goal in the most efficient manner using structural analysis techniques. That's a good thing about doing structural type analysis, either in a predictive or reactive way. A company, an organization only has so much money, resources they can spend. Where's your biggest bang for your buck? What can you do to most improve your safety? And that's what we're trying to get at. And you've seen these definitions. Causal factors, reading the root causes. All right, let's change gears a little bit and talk about analyzing data. When we do a root cause analysis, there's a lot of activities that take place. We try to do a timeline and say what exactly happened when. We interview the different people. What did you see? What did you see? What happened? We go back and look through the logs of the control room. Maybe there's some computers that we go through and look what happened in the system over a certain amount of time. A lot of work that we need to do. Sometimes we have to analyze the data. So what we're going to talk about this evening is something that's near and dear to my heart. I've done a lot of it. Fault tree analysis. Anybody ever, do you get into fault tree analysis? This is the time. All right, we're going to talk about fault tree analysis. It's mostly used, it started back in the 1960s. I think Bell Labs started it on the Minuteman, which was a missile program. What can potentially go wrong? So NASA, the nuclear industry, things with a lot of redundancy, and it's getting more and more in the chemical industry. What are the combinations of failures that can give us the top event that we're trying to avoid? So that's what we're going to talk about. And yes, we have to do data analysis as part of root cause analysis. So what do? We talked about this already. Causal factors, work our way down, identify the root causes. What are the recommendations? So that if we look at, and when I say fault tree analysis, cause and effect tree, it's essentially the same thing. So that's what we're going to talk about mostly tonight is cause and effect trees and why they are good and looking at events with lots of things going on. Timelines are good as well, maybe more so for people-oriented problems. Bill did this, Sally did this, and then Ed came along, and that's how the whole thing went. So you go step by step and see who did what when, and that's a timeline. Causal factor charting is kind of taking that root cause thing back there and working down and seeing what the root causes are. But we're going to talk about cause and effect tree for a little bit. It's good to have all the techniques. It's good to have all the methods out there. And so that's a good thing about going through a course like this. You're going to learn a lot of different techniques over the semester. Is any one better than another? Not necessarily. I've heard it said to the man with only a hammer, the entire world is a nail. You need a saw, you need a wrench, you need a screwdriver. You know, you need all the tools. And as engineers, you need as many tools as you can, at least know where to go get someone who knows how to use that tool. So this is an example of cause and effect tree. A spill occurred from tank 45 during transfer of the storage tank. So, and we'll show you the system here in a little bit. It's a big tank in a, what they call a containment. It's like a dike around it. So if there's any releases, it's contained by the dike and doesn't go out into the environment. So that's an OR gate there. And what we're saying is we don't know exactly what happened, but we're looking at the system and we say, all right, it could be one of three things. It could be that the tank failed, piping failed. That's a possibility. It could be that we filled it up during our filling operation, that we screwed up and overfilled it. Or it could be that there's a sampling line off to the side. Maybe that overflowed. So what we're trying to do is go from the general down to the specific. What are the potential ways that this happened? Looking at tank failure, it could have been the tank failed, could have been piping, excess flow during filling. Maybe that our pump went crazy and the pump had to overspeed, pumped too much stuff. Maybe we filled it twice without emptying it. Keep that in mind. Or the other thing is an AND gate where we had a valve that was misdirected. We had two valves that were in the wrong position. One should have been open, was closed. One should have been closed, was open, caused the flow to go through. So looking at all that and looking at our system, Our system is we fill it up at the top. There's an overflow line that goes into the dike or the containment around it. There was some work going on off here to the side, and there was a sample line. That should be connected like this all the way through that sample line. It could be that this valve was closed and this valve was open, and so we had a leak going out through that. We don't really know exactly what it was, but we're going to do some analysis and see. I think I did it right that time. All right. It turned out we could go to our computer printout, and it showed that here's the blue line is the level, the red line is the flow rate into, and the green line is the flow rate out. Well, guess what? At 9 o'clock, we filled it up to 80% of tank level, and then at 10 o'clock, we tried to fill it up again, and it never went over 100%. Why? Well, because it's very simple. It has an overflow and it went into the container. So our mistake was filling it up twice. And so that we were able to go through and draw this cause and effect tree, look at all the potentials out there, and come up with a reasonable explanation of what happened. Because a lot of times you don't really know. There's lots of different things out there that could occur. All right, so that's a very simple cause and effect tree. So let's talk about some of these symbols. The rectangles are events. It could be a top event, intermediate event. We work our way down through the gates. Gates and gate, this and this have to happen, or gate, this or this have to happen. There may be causal factors, items of note, and that's just the events, the lower level events that have led to the top level event. We usually begin at the top, work our way down. These can go on for pages and pages and pages, but we sometimes have to transfer symbols to go from one page to another, et cetera, et cetera. AND gates. For an AND gate to occur, you must have multiple elements must be present, multiple pathways may be in a specific state, redundant equipment must fail, safeguards must fail. So two things have to happen in order for us to have the top event captured. That's an AND gate. Here's an example. Say we have a fire. What's the fire triangle? Anybody know the fire triangle? Fuel, air, and ignition. Yes, that's right. This one has to be with a vapor that's releasing. The mixture was too rich or too lean. So in the incident that we saw was a big fire and explosion. What was the fuel? Vapor from the oil, right? Ignition, oxygen was everywhere. So we were set up to have a fire event. It turned out that the vapor coming out was at the correct or the incorrect mixture such that it was easy to ignite. So that was satisfied the AND gate of having all the situations where a fire could occur, unfortunately. It might be something where if you say you have oil going to an oil port, you have to a gearbox, you have multiple pathways, all three of them have failed. It might be that you have a whole combination of valves that have to be in the wrong position. It could be, and so this happens a lot if you have multiple safeguards and they've all failed. So that is when we use an AND gate. One more, it might be a situation where you have an imbalance and your vibration backup fails. So you have a case where you have an initiating event that could cause the incident and a failure of the safety. AND gate. One more, just a combination of human errors. OR gate is any one has to occur. Any one of those can go forward to the top event. Some examples are if I said I had a piece of electronic equipment is damaged because of environmental problems. It could be temperature, humidity, what's the other one? Vibration. We don't know what it is, any of those. It could be that we have several different tanks and we say, well, I have a release. Well, it could be like saying I have a flat tire. Well, you have 4 tires that you potentially have a release from. It could be that I've got redundancy and I have an inadvertent trip. So that if you have 2 things that could shut you down, either one of them could shut you down. That's why in a lot of these instrumentation systems for chemical plants, nuclear plants, they have what they call voting logic, so that any one can't shut you down. Usually it's like 2 out of 3. So the very detailed, highly redundant systems often have a voting logic to them that you can analyze using a cause and effect tree. Common cause failure. So let's talk about that. Is the thing that keeps risk analyst people up at night. Can anyone guess what a common cause failure would be? Nobody? Really? I'll tell you a true example. All right, I've got a big camper, 5th wheel camper. I went down to Georgia for the football game. All right, I have 2 Honda generators, you know, the quiet Honda generators. And so sure enough, we cranked them up and got the air conditioning. It was still hot and it was working fine. And we come back from activities and they stopped. You know, 2 separate generators, they both stopped. And they were like 3 years old. Crank, 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 crank. Nothing, nothing, nothing. And so I took them to the shop back here in Tennessee and they said, bad gas. I had gas that I used for my 2 redundant generators, but it was a common cause failure that caused failure of both of them. So that's what we mean by common cause failure. You think you have redundancy, but there's a common link. There's something that can destroy both of them. Off my thing. Okay, I'll just hold it like this. So here is a fault tree for performance procedures performed incorrectly. It could be a series of steps. Sometimes we have steps and procedures that act as a backup. So we're saying we have failure of step 3 and failure of step 4 to detect the error that we have. So that's kind of what we're getting at with these cause and effect trees. Common cause failure. I just talked about the one with my bad gas. It turns out that some systems you think are redundant, you work your way through it, and there's something like an electrical bus that serves 2 redundant components. Then you don't really have redundancy, and you have the common cause failure that occurs. That's what we try to look for. And then here's a fault tree, cause and effect tree for a human error with recovery possible. So a lot of times if we have a human error and you have a potential to detect the human error and a potential to correct it. So we can take that into account in our trees as well. This is just a tool for going through and helping you decide, do I really have the logic right? But really, what you do is you work your way from the top down and say, what potentially could happen at the next intermediate event, so forth and so on. Examples will help you. We're going to go through an example here in a minute. Yes, you have to go through and test your OR gate logic, make sure that it's correct. We won't go into that. Same thing for the AND gate. So here is just a sample cause and effect tree, and more used for the root cause, where we say, all right, we had a problem, we had inadequate lube oil cooling. Why? It could be that we lost flow in one branch. It could be that it got too hot. It could be that our coolers just weren't working. Or it could be that the cooling demand was beyond system capacity. So what we did is we went through and we drew this tree, a fairly simple tree, And we said, how can I prove these branches are correct or not correct? So the first one we had was loss of lube oil flow in the branch. Measure the flow. Use a gauge. Make sure, we getting the right flow? Second, is there external heating? So go look at the line and say, is there something else going on there? Is there some heat source we didn't know about? Coolers are functioning. Measure the output temperatures. Are these coolers working the way they should? The last one is, have we just not designed for the system? Had do a calculation and say, are we meeting the demands of the system? So it turns out for this one, we go through all these different things and we find out that yes, we measure a 3-degree difference in the primary cooler and a 5-degree difference in the emergency cooler. So we have failure of our coolers. Well, no kidding. So that's why there's instrumentation to make sure everything in the system is working okay. This is just a way of going backwards and saying, what do we think the problem really was? Our coolers weren't working appropriately. All right. So a lot of times if you draw these trees, maybe you do it as a group, you can use sticky notes and start at the top, work your way through. There's software packages out there. I use a package a lot called Sapphire. It's sponsored by the Nuclear Regulatory Commission. It's a good package for drawing fault trees. Lots of different things out there. You could get into more detail, especially doing a predictive type of an analysis, where you look at the individual equipment, human error failures, come up with failure rates for those, and you can come up with an estimate of the overall failure of the top event. That's typically what fault trees are used for, mostly in the nuclear industry, but we're also using it a lot in the chemical industry. I know that you're doing some reliability analysis, so it's just on steroids because you're doing it for an entire system, not just one piece of equipment. So let's talk about this problem, circuit problem that we're going to work in class. Hey, there it is. Okay. So it's a fairly simple system. Any electrical engineers in here? None? Really? Okay, you know electrical engineering. So most of the world, they're called EEs. Here they're called LEs, electrical engineers. That's your joke for the night. I'm not much on that. All right, so anyway, it's a simple system. The motor has to run for 20 minutes to fill up the tank. If it runs for 24 minutes, the tank overflows. So what happens is the operator goes around here, he closes this switch. When he closes this switch, energizes the circuit starts a timer relay. This timer relay runs for 20 minutes and then it opens. When it opens this relay and stops this other circuit where the power goes to the motor. Stops the pump, we don't overfill it anymore. So that you look at the operator, he or she is also a backup. He watches the tank. If the tank overfills, comes over here, opens the switch, cuts off the power to the relay, and the power here as well, cuts off the power to that relay, the motor stops. So if I said, okay, draw a cause and effect tree for this problem, what would be a question you might ask? Have I told you yet why you're drawing the fault tree? What's the top event? What are we drawing the fault tree for? Stephen Covey said, begin with the end in mind. For this particular problem we're doing in class, We are worried about the top event is motor operates too long. We overfill the tank. So once we know, oh, that's why we're drawing this tree. So our top event is motor runs too long. And top events have to be very specific about the system and what the failure mode is. Motor fails too long. Motor runs too long. Okay, and we give you some guidance here. The motor drives the pump, fill rate 4% a minute. If the motor operates too long, tank overfills, start the system, operator closes switch, energizes. The relay is set before the tank overfills. The contact should stop the motor. Operator is instructed to keep the eye on the liquid and then open it out, or it times out. So we start with the top and we give initial conditions. We're saying our initial conditions are this switch is closed, this relay's closed, this relay's closed. So we're operating. So we have to think about how we start to realize how we're going to go through and do this. Okay, so I'm going to go through and talk about this, and then we're going to have homework. Don't blame me, she told me to give you homework. Okay. So here's the problem. Motor runs too long. Could be that the relay just sticks by itself. So we've used an OR gate here to look at the combination. We say it could be the relay has stuck in the closed position, or it could be that the relay is energized too long. Let's go back and look at our relay. We're saying this relay right here is energized too long. That is, we've gotten to the point where the tank is full, it should be released. All right, what commands this relay? The timer relay, right? So that if this timer relay is closed, we're getting a circuit to this. Once we release it, it should open. So we're going to look down at all the ways that this relay can be energized too long. And we've said that that's an AND gate because there could be different things that go wrong. It could be the timer relay is closed too long, or it could be that the switch is closed too long. So we have some redundancy here. We're depending on a piece of equipment, the timer relay, to release after 20 minutes. If that fails, the backup is our operator who opens this switch and kills any power going to this. So there's two ways that that relay should be de-energized and allow the motor to stop. Okay, what else could go wrong? Well, we got to go down one path at a time. So if we go down the timer relay path, well, yes, that timer relay could stick closed. Or it could be that it was commanded closed too long. Why is the switch? That switch may be closed too long because maybe the switch itself failed, or maybe the operator failed to recognize that the tank had overfilled. If we work down the other side of it, why did the timer relay go too long? It could be that the timer itself failed, it went too long, or it could be that the operator failed to de-energize the timer relay. Which turns out, you see this part of the tree, the switch closed too long, switch is closed, or operator fails to open switch. It shows up here too. So when we think we have some redundancy, actually those two things show up on both sides of an AND gate. So you have to be careful as you go through and examine your systems to make sure that there aren't any common type failures that can occur there. So that was just a real quickie fault tree. Now what we would like to do this as a homework problem, right, is what if we said the other problem was that the motor fails to run? just off the top of your head, what would cause that motor to fail to operate? The relay doesn't close. Thank you. Yeah. What else? We haven't talked about it for the others. Power supplies, right? So you have to think about, when you think about a problem, your top event completely changes, then that changes your cause and effect, your fault tree. So that's the challenge to you, to go out and draw a fault tree on motor fails to operate, that we don't get any pump. So same problem, same circuit, different problem. Okay, this is how I should have done it, and go through all these details here. But you get the idea. Okay, so there's other types of analysis techniques that we do. HAZOP, failure modes effects analysis, target analysis, so forth and so on. Lots of different things that we do. All I did was just show you a little snippet of things, cause and effect tree. So results of the data analysis, maybe we use a cause and effect tree to go backwards and say, what really happened here? What do we think happened here? What is the causal factor that we can point to come up with the root cause, improve our system? Key points to remember: data analysis, we're trying to identify what these causal factors are, and we're trying to work down and see what the root causes are. Equipment and failures are usually analyzed with cause and effect tree. That works out very well. Timing is an issue. Maybe you might do a timeline type chart. So here's all your homework, right? We're going to give you some papers to read, and there's another explosion event where you can go through and identify what you think the causal factors, root causes are, and the fault tree that we assigned you. So what is the failure of the motor? So that's all I had to say. If you guys have any questions, I'd be glad to answer them. Otherwise, I've enjoyed talking to you, and we'll see you at the football game or something. Okay, thank you. Thank you. You would like the microphone.
Just a very quick announcement. All right, so we are gonna give you the homework as usual, right? In our homework format and everything. Just a quick note that next Thursday is Engineers Day, so I want you to get involved with all the activities that are planned for that day. So no class. We are gonna reconvene in 2 weeks, but then so homework is gonna be everything. Homework and quiz will be assigned a week later, right? So that it's leading up to the time that you come to class. So don't look for homework tomorrow. So you're going to be posted. The homework is going to be posted next Friday. Quiz is going to be posted 2 Mondays from now, right? Leading up to class. Thank you. Have a good one. Just a second.